Hello everyone, I am Ankur Shah, Assistant Professor in Department of Civil Engineering from SKT, Jaipur. Today's topic is analysis of space frame by tension coefficient method. Space frame or space truss is a three-dimensional assemblage of a line member, each member being joined at its end to the foundation or other members by frictionless ball and socket joints. The simplest space frame consists of six members, and these six members join together and form of tetrahedron. This tetrahedron look like this. A stable space frame can be constructed by a successive addition of three new member and a joint. Okay, in this figure we can see at every joint there's a three member joint. Okay, the original tetrahedron consists of six members and four joints. Since for each additional joint, there are three additional members. So if we can see in this figure, suppose there's a joint, we need to construct another tetrahedron or other series of space frame. We can join three members at particular this joint. Okay, just like this, we continue to join three members at every joint. The relationship between the number of members and the number of joint can be expressed by this equation: n minus 6 equal to 3j minus 4. 6 because we have 6 member and 4 because we have 4 joints. So concluding this, n equal to 3j minus 6. I think you all are familiar with this equation because we use this equation in indeterminacy of the structure. When we use this equation to find out the indeterminacy of the structures. Okay, this equation gives the minimum number of members required to build a stable truss. Okay, if n equal to 3j minus 6, this will give the number of members which will be required to form a stable truss or frame. If it is less than, it means it is unstable, or if it is more than, then it means it is indeterminate structure. Okay, there are two figures. In both we can see the space truss. This space truss used where we need a larger area with roof without columns. Okay, just like stadium roofs. Okay, tension coefficient. The tension coefficient for a member of a frame is defined as the pull or tension in that member divided by its length. So small t is equal to capital T upon L. Small t is equal to tension coefficient, T is the pull in the member, L is the length of a member. Okay. So consider, okay, before considering a member, first we choose a plane, the XY plane, and now consider a member AB. Okay, A1 and B1 are the reference point on the particular X and Y axis, and Y axis A2 B2, and at X axis is A1 and B1. The coordinates of A and B point will be: at A is XA comma YA, at B will be XB comma YB. Okay, suppose AB, member AB is pin jointed perfect frame and in an equilibrium condition. Okay, and this system is under a external force or a reaction. This external force acting at a joint. Okay, suppose TAB, capital TAB, be the resultant pull in this member, this one. Okay, and these are the direction member. So component of pull TAB in direction of X will be TAB cos theta. Okay, and should be equal to cos theta will be AC upon AB. So it will be TAB bracket AC upon AB, and in AC we can write this XB minus XA because A and C in the same plane. Okay, there's a no distance in Y direction, so Y, all there's a no coordinate in Y, so the value of AC will be XB minus XA. If the C is the coordinate of C is will be XB, so AC will be XB minus XA, and AB is LAB. LAB means length of member AB. So it should be small TAB bracket XB minus XA, where TAB is the tension coefficient for member AB. So overall TAB upon LAB. Okay. So we can say that the component of force in the member along the X and Y direction can very easily expressed in the term of tension coefficient. So the length of the member AB will be equal to under root XB minus XA square plus YB minus YA square. Okay, there's a normal tension coefficient method, but we need to use this method for the analysis of space frame. Okay, so now the method of tension coefficient applied to the space frame. For the space frame, we have to use a 3D frame, okay, or a 3D figure for the analysis purpose. For this, we use a cuboid. In this, we choose to member AB, of course, in direction X, Y, and Z, and we choose the inclined, this line AB inclined at the angle theta X, theta Y, and theta Z. Okay, so length of AB member in 3D frame or in 3D space will be equal to XB minus XA square plus YB minus YA square plus ZB minus ZA square whole power 3 by 2. Okay, M, N, and L. These are the directional directional points. Okay, in cosine directional points. So in direction, cosines are LAB. L AB member in L direction will be cos theta x, AB member in M direction cos theta y, and AB member in N direction, which is NAB, equal to cos theta z. Okay, so the component of AB along x, y, and z axis are AL equal to XB minus XA, because AL in only in x plane or in x direction. Okay, so XB minus XA equal to AB cos theta x. AB is equal to, AB is the member equal to length AB, and cos theta x is equal to LAB, just like previous equation. Same as AM equal to YB minus YA equal to AB cos theta y. So cos theta y is equal to MAB, and AB is equal to LAB. And same as AN is equal to ZB minus ZA equal to AB cos theta Z equal to NAB dot LAB. Okay. Now the because of the external forces, there's a resulting pull in the member AB is TAB. So resolve the component of force TAB along X, Y, and Z direction. That is same like before. TAB cos theta x is equal to TAB XB minus XA. LAB equal to TAB XB minus XA. That's only in X direction. Same as if we use theta y, that will be theta AB, YB minus YA. If we use Z in Z direction, it will be small TAB, ZB minus ZA. Okay, we need to resolve this resultant force in each direction, in all three directions. First goes to for X, then Y, and last one is Z. Okay, Z1 is vertical direction. Okay, let PA be the external force at a joint A, and XA, YA, and ZA be the resolved components. Okay, let AB, AC, AD be the member of meeting at a joint, just like this. Okay, suppose there is a member AC, AB, AD, all three members jointed at point A. Okay, we all know if we want any member be in equilibrium condition, so the sum of all the resolved forces should be zero. The same principle we used here. Okay, so since the joint is equilibrium, the under the external load of force and the pull in the member meeting at a joint A, the algebraic sum of resolved parts of these forces in n direction must be equal to zero. Okay, from this we got the following equation from the for the point or joint A. Okay, first one is T small TAB XC minus XA plus TAC XC minus XA plus TAD XC minus XA plus 2XA. Okay, same as for the Y direction and same as for the Z direction. Okay, the X, Y, and Z are the external forces. Okay, this is the equation we used to analyze the space frame. Okay, we can write this in compact form. This is summation of T xf minus xn plus xa, same as for the Y and Z. The F and N are the far end or the near end, okay, of the coordinates of each member fitting at a particular joint. Okay, so these equation we used to analyze this space frame. Okay, now we take a question for analysis purpose. The question is, a pair of shear lag has a length of each lag as 5 meter. Okay, and the distance between their feet is 4 meter. The line joining of the lags is 7 meter from the foot of the guy rope. If the length of the guy rope is 10 meter, find the thrust in each lag and pull in the guy rope when the load of 100 kilonewton is suspended from the head. Okay, so first we need to draw a figure. Okay, obviously we have three directional truss frame. So there's a two shear lags. The distance between them is 4 feet. Oh, sorry, 4 meter, and the each lag length of 5 meter, and the a guy rope which is length is 10 meter. Okay, so if we name this figure, and 100 kiloton load act at the head of the shear lag in downward direction. Okay, so first of all we write like this. So if the middle point is C, we have the direction, we have the distance of AH, BH, OH. Okay, but if we have to solve, we have to also find the value of CH and this angle theta. Okay, so first we find out the value of CH. For CH, what we do? Under root AH square minus AC square. Okay, and if AB is 4 meters, so AC will be 2 meter. So it should be like this: under root AH square minus AC square. So AH is equal to 5 and AC will be 2. So 5 square minus 2 square is equal to 4.58. Then we have to find out theta. Okay. For this, what we do, we need to use a triangle. Triangle will be O, C and H. This is the triangle we need to use. Okay. So and use cos formula. Okay. So from triangle OCH, cos theta will be equal to OH square plus OC square minus K CH square upon 2 OC into OH. From this we solve, theta will be 23.9 degree, and we finally calculate the sin theta will be 0.4051 for the further calculation. Okay. Now drop a perpendicular HD on y-axis. Okay, just like this. Drop a perpendicular in direction of load. Okay, this is point D. So now we have to calculate all the distances. We know about OC, OD. Okay, so OD is equal to, OD will be OH cos theta. That will be, OH is 10 meter length of guy rope. So cos theta will be uh, so 0.9143. So 10 into is equal to 9.143. Now HD is equal to OH sin theta, that is 10 into 0.4051, and CD will be OD minus OC. So 9.143 minus 7 is equal to 2.143 meter. Okay. So we have all the distances. Now, so we have to point out all the coordinates of the points. Okay, or the junctions. So the conjunctions or the coordinates of points O, H, A and B. So point O will be 0, 0, 0, and H, OD will be, what is OD? 9.143. So at H is equal to 9.143 and Z 0.451. Okay, HD distance. What is HD? HD is 4.051 in the height, and OD will be in Y direction, Y plane. Okay, that will be 9.143. So the coordinate of H is 0, 9.143, comma 4.051. Same as like A and B. A is minus 2. Okay, from the Y plane, it is in uh, above the other coordinates, so it will be in minus, and B is the positive coordinates, so it will be so there is a positive value of coordinates. So at point H, the equation can be written like this: THA xb minus xa plus THB xe minus xa plus THO xt minus xa plus xh. In the derivation, we analyze the joint A, but in that figure we used point at H, point H. So we write the equation as a H in H form. Okay. Now substitute the values of coordinate in equation 1, 2, 3. Okay. So if we put the values of coordinates O, H, A, B in equation 1, we find out at first THA plus THB equal to 2, this is equation number 4, minus 2.143 THA minus 2.143 THB minus 9.143 THO equal to 0. That will be equation number 5. And for the equation number 6, 4.051 bracket THA plus THB plus THO sorry for this. This is T H O minus 100 equal to 0. That's equation number 6. Okay. So from equation, and there's a 100 the load. Okay, and x-axis and y-axis is equal to 0 because there's a no load in direction. The 100 kilonewton load act in only in that direction, and minus because of the downward direction. From equation number 4, TH is equal to THB, and from equation number 5, we can calculate like this. THA will be equal to minus 2.1332 into THO, and from the equation number 3, minus 4.05 minus 2.1332 minus 2.13 plus 1, THO is equal to 100. So THO will be 7.5573. Okay. Now THA will be equal to THP. So THA will be 2.1322 into 7.5573. Okay, and it will be equal to 16.122. So pull in the gyro, okay, will be equal to THO into length. THO will be tension coefficient and at length HO, and the L is the length of HO member or the guy rope. So tension coefficient for this member 7.2273 into 10. 10 is the length. So it will be 75.57 kilonewton. The force in the each shear lag will be equal to 16.122 into 5. What is 16? 16 is the tension coefficient in this member, into 5. 5 is the length. So the force in each shear lag will be 80.16 kilonewton. Okay, this is the analysis of space frame by tension coefficient method. Thank you so much.